Hello, everyone. Today I want to talk a little bit about my project over greedy algorithms. I'm going to be looking at the knapsack problem, of course, and I'm sure you all know the two types, the two main types of knapsack problem, the 0, 1, and fractional, and that the greedy algorithm works very well for the fractional knapsack problem. It's very fast for that. It's very simple. Now, I'm actually not going to look at the fractional knapsack, and the reason is it's trivial to do a fractional knapsack problem. There's just an extra step basically at the end of the greedy algorithm. Uh, but I'm just going to compare the 0, 1. And when I do that, it means that the greedy algorithm will not most of the time find the optimal solution. But I wanted to compare apples and oranges, and I'm looking at the performance of the two of them. I'm not so much concerned with that particular factor. When you add in that, it doesn't really add. When you add the fractional knapsack problem, when you put it in those terms, it doesn't really change performance much. It's one extra step. It's not a big deal. So let me go ahead and start by looking at my code real quick. And here you can see I first created a kind of a brute force version of the knapsack problem, and it's recursive. It's very slow. It looks at every single combination to find the optimal solution. It will find the optimal solution, but it's extremely slow. Here's the dynamic version. It was so slow, I didn't even include this in any of my tests. It wasn't really worth looking at. I mean, it's fun to look at, but it's just, I don't know, it's extremely slow. But when we get down here to the dynamic algorithm, it's a little more interesting. It can obviously find the optimal solution, and it does it in way fewer steps because it doesn't have to look at every sub problem when trying to find the optimal solution. Now, I did change one thing. Originally, this is an algorithm I pulled off the internet. Most of them will look pretty similar to this, varying by whatever language you use, but the logic's the same. Instead of using a two-dimensional array, I am using a jagged array. So it's an array of arrays. And I did that because the .NET platform is .NET framework, which is actually .NET 5. They don't really call it the framework anymore, but in .NET 5 and other types of the .NET, it's optimized for single dimensional arrays. So two-dimensional arrays, of course, are fine. They're just not as fast. But when you do an array of arrays, you can access the sub-arrays as if they're just single dimensional arrays. So indexing them is way faster. And I did find there was a pretty good performance difference. I didn't actually show that any of my testing. It wasn't really part of this, but it definitely changes the performance. So anyways, I did not use a two-dimensional array. That's really the only change here. Otherwise, it's pretty straightforward. And then my greedy algorithm is pretty simple. I just came up with this one on my own because it's so simple. The only thing I want to hit on is that all I'm doing is taking I'm not taking the a list, and I'm doing an order by descending, and for my what's the word I'm looking for here? Basically, the way I'm sorting it by is taking the value divided by weight of each item and sorting it on that, descending from greatest to lowest. And that's basically going to give you your value weight ratio. And the reason I did this, I didn't want to actually sort the items inside the list. I just wanted to be able to iterate over those sorted items. So order by just returns an enumerable, which lets you do a for each over it. So it'll go through every item in it, every ordered by item in it. So anyways, all we're doing is checking, we have a value for weight. We're storing the overall weight of items as we consider them part of the knapsack. And if the weight that we have so far is plus the item we're trying to add is less than the capacity, we go ahead and add the item to, or add that weight. And we also add the value to our overall value. And once we get to the point where we can't add another item and be within the capacity, then we go ahead and stop there and keep trying more items. Once we're done looking through all the items, we'll then return the overall value. Pretty straightforward stuff. Now, if we wanted to do fractional, of course, we would add an extra step for the last item of the highest value to weight ratio that doesn't fit. We then take a fractional portion of that and add that to our knapsack. Now, to do that, it's very straightforward. But I chose not to do that because I wanted to see how far off the greedy algorithm is from the dynamic programming algorithm. So looking at my tests, I do the validation on here, and it's kind of fun because I know that with the values I have, it is going to fail validation for the greedy algorithm. And that's fine. I still do the test. It's just interesting to know that the brute force and the dynamic both return an optimal value. Greedy does not. Now I could pick numbers on here where it would make greedy also be optimal, but let's go on here. That could be a failure of my little validation, honestly, because it depends on these values. You could pass or fail just depending on which values you have here. So it's not really a true validation, I guess you could say. There's cases where it might validate and cases where it won't. Most of the time it won't, though. So anyways, moving on along. The way I conducted my test is actually to do two tests. One, and this test, this right here, it's all these numbers on here. What's going on here? Well, it's calling this this test function here, where we just have some parameters for iterating over the number of items that are in our source of items that can go into the knapsack. And that gives us like the minimum, the maximum, and then how much we want to increment it by. And then we also have one for doing the same with capacity, how the minimum capacity we want to have, the maximum, and then how much we want to increment it by. And I did this for two reasons. Well, for one reason, I wanted to be able to look at, compare the performance of increasing the number of items we're looking at, and also compare increasing the size of the capacity, the weight capacity of the knapsack. And I did that because on the dynamic programming algorithm of the knapsack problem, the complexity, the time complexity is big O N times W. And when I say N times W, we're looking at number of items times W, the weight capacity. That's, you'll see W used most of the time in the examples. And that means theoretically it should increasing the number of items should add the same amount of execution time as adding more capacity. It should be equivalent because it's multiplicative. Wow, it's hard to say. Multiplicative. Anyways, so you increase either one, it should have the same result on performance. So I kind of wanted to look at that and see how if it actually works out that way. Now, the greedy algorithm, I was curious as to what its performance looks like in comparison between adding more items versus adding more capacity. There's a lot going on in here. It's a lot of this is formatting to give a nice, pretty output on the screen. But we're just we've got a loop. This first loop here is for actually incrementing the number of items. The second loop is for capacity. Each time we try a different capacity, we create a new random list, and both algorithms will get the same random list. And now right here, one more loop. I'm testing each list of values, each data set 10 times. I've also bumped it up to 100. It just takes longer to run. And that just lets me take the lowest value of the two, which that's what's going on here. It's taking every time the value of duration for dynamic or greedy is always going to take the minimum of what it currently has and what the current test, what the last test had in the current test. So it's always going to pick the lowest score, because any noise that's added is only going to slow the performance down. And we're looking at what the ideal situation is. 10 is not really enough to see that. It'd be better to have more, but it's good enough for my purposes. And then more stuff for formatting the output and everything. It's just making the numbers lined up nice and pretty. And I got some stuff in here for changing the color. And that is for if the greedy algorithm is the exact same solution as the dynamic, then we're going to print it out in green because it's 100% accurate. Or if it's not, which is most of the time, it's going to be red to show that it did not pick the optimal. And we'll see how it plays out, how close it's going to be. And I'll give you some reasons why I have the results I do. And this is just a little helper function to give us a random list items. So that's pretty much all there is to it. Shoot, it's probably gonna take this thing a while because I just fired up Visual Studio. We'll go ahead and run it. Let's see what it says. Oh, I probably gotta set yeah, I gotta set test console as the startup program. Oh, I gotta open the actual solution. I'm just looking at the directory store. This laptop's kind of slow. It's an old Alienware. Painfully slow. All right, let's look at, okay, we got this says, yeah, we do. Let's try this again. There we go. Now, so when it runs, it's going to get started. And as you can see, it will have the count capacity. The count is the iteration number we're on for count. Capacity, of course, the first test, we keep capacity at 1,000. And we're only iterating over the count. Dynamic time, that's how long it took to execute the dynamic algorithm. Dynamic max, that's the max value, optimal value we received from the dynamic algorithm. I just want to keep up and scroll up. It's going to drive me crazy. So on the greedy time, that's also, there we go, select some things. Greedy time, that's how long it took to execute the greedy algorithm. And then max is its optimal value, that or the value it found as being the max value. And then percent of optimal, that's how far off from optimal the greedy is. If it's 100%, it's dead on. Otherwise, you'll see here lots of 99s, all those pretty numbers. It looks like it's so close, it's doing so good, but actually there's a reason for that. It has to do with the number, the range that I'm using for the items in my list. It's picking values from any range. If I limited it to only larger items or larger weights, it would have an impact, because there'd be less likely to find one with a good value that also fits. Because when there's so many random values in there, it's easy to pick the perfect ones to kind of almost fill it up. So that's why it looks like it's always close. But depending on the data set, it could be pretty far off the greedy algorithm. So let me switch over to Excel, and let me open up. Okay, and this is the results of a test I did, and this first graph is showing, this first chart is showing for 1,000 weight capacity, it's showing how much execution time there was for various number of items from 0 to 10,000. And as you can see, it's a very linear line here. It's now there's a little hiccup here, and that kind of, this happened like every time. No matter what I did, it would happen at around the same area every time, guaranteed. I tried it so many different ways. That's one of the reasons I changed from the two-dimensional array to jagged arrays, and it still has a performance hitch right here. It's kind of interesting, but it might be something with garbage collection. I even tried having forcing garbage collection doing a GC dot reclaim. Was it reclaim? Anyways, GC dot collect to do a garbage collection before each run of the algorithm. Still didn't help. But anyways, doesn't really matter. I put a little trend line on here so you can still see. And if you notice, it ends right around 30 milliseconds. And I'll get to that in just a moment when we look down here at execution time for a fixed number of items at 1,000. And instead, we're incrementing the weight capacity. And if you notice, it's also a fairly nice linear progression. It still has this little, you see the hiccup here as you start increasing the capacity. It also has a little glitch, I guess you could say, but it recovers. But anyways, I put a little trend line here, but if you notice, it also at 10,000 is right around 30 milliseconds, or right around 30 milliseconds. So that tells me that whether you increase the number of items or whether you increase the capacity, it has the same effect on the dynamic algorithm. And that's exactly what we expected, because it's big O N times W, and worked out perfect. And I was very thrilled that it worked out as well as it did. Very close. Over here, this is just where I broke out only looking at the greedy algorithm, because you can't really see much in these. Now this one, you can see a little bit of the performance take a hit as it goes up, but you can't really see, and you can't see anything on this one. But looking here, and I put a progression line. You don't need a progression line for this. You can see it's basically a straight line. But yeah, it works out pretty good there. Nice linear line, and then a linear line. Well, whatever. Get down here to execution time of the greedy algorithm for fixed number of items, progressing the capacity, iterating over the capacity. It's really random, a lot of noise. So I put in, this is where I really needed the trend line to kind of see that it is slowly slowing down over time, and it's linear for the most part. It's just a whole lot of random noise. Why is there so much random noise? Well, increasing the capacity, just really, there's a lot of randomness to the data and fitting items in there, and it's just, you get a lot more noise on that than when you're just increasing the number of items but keeping the capacity the same. I'm not 100% sure why there's so much noise, but it works out that way every time. It might just be mostly because we're seeing more detail, because this is only going from 0.1 milliseconds to 0.12 milliseconds. We're up here, we're going from close to 0 milliseconds up to 1.6. So that's actually, I'm pretty sure that's why you're seeing a very, very small range here. So you see all the little noise that kind of gets hidden away. But my conclusions kind of held true, that the greedy algorithm, or my predictions, the greedy algorithm would perform much faster than the dynamic programming algorithm. Oh, let me show one little thing here. Scroll down. This number right here, you just want to see what you're looking at. It's just a copy and paste of what's inside the output of the program. This is the average of the percentage difference between the dynamic and greedy algorithm. The average I got for that run was 99.84%. That's misleading. Yes, with pseudo random numbers and picking a range, a very broad range of values for weight and for the values of each item, yes, it gives you a huge number of items with to pick from that fit in the scenario nice and neat for the greedy algorithm. Real world data might not work that way. So the greedy algorithm might not, it likely wouldn't be this good, performing this close. You can easily pick numbers manually that will make it horrible. But I kind of want to explore that a little bit because, in some situations, you might not need the perfect, absolute best solution because you need to get it fast and you don't have time to wait on the perfect solution. You need one that's good enough given the time. Now, some situations you need the absolute best, but it's not always the case. But I just thought it'd be kind of fun to look at that with the greedy algorithm, because if you look, can you use the greedy algorithm for a 0-1 knapsack? No, you can't. It will not work. But you can do it. You're just not going to get the optimal result every time. It might sometimes, but it's fun to look at. So does it technically solve the problem? No, but that's okay in my case. And honestly, changing this to fractional is almost feels like cheating, because you're now changing the parameters of the problem just to fit the greedy algorithm, which is fine. But anyways, that's kind of the results I got. I had a lot of fun on this one. Unfortunately, this is the second video I had to make. My first one, no audio was recorded, so I had to do another one. Yay me. So anyways, I hope everybody has a great day and had fun with their projects, and I'll see you next time.